In this video, we will discuss real-time video scene classification for underwater applications.
Our objective was to create a system that can classify multiple moving objects in real time from video streams, even when the scene is dynamic.
In real-time video scene classification, little work has been done on underwater scenes.
To automatically classify objects that appear in video streamed from underwater sources, separating a dynamic scene is required. Objects in the foreground also need to be separated so they can be classified individually.
Traditional approaches to foreground extraction are based on the assumption that the camera and the scene are static. This assumption is not true for video from underwater sources, as both water currents and desired movement all lead to the apparent motion of background objects.
Other challenges with underwater video include sun glare magnified by the motion of the water surface, which casts rippling caustics onto both foreground and background, bubbles, floating particles, surface debris and their shadows, and the hue of ambient light, which changes with depth. All these things are unique to underwater video and must be accounted for by the system.
Our processing begins with background estimation. Background estimation keeps track of the background of a series of frames so that when a foreground object enters the video, we can quickly identify it as such.
We coded two background estimation algorithms, a common filter and a Gaussian mixture model, and used each to extract the foreground from underwater videos. As you can see, while each of our two algorithms does a decent job at identifying the foreground of the video, they both have their problems.
Common filtering often leaves ghosts or portions of the background that the algorithm erroneously classifies as foreground after a foreground object stays in one spot for too long.
In contrast, the Gaussian mixture model contains more noise, speckling the extracted foreground with misclassified pixels.
The fusion of the two algorithms, in which we only include pieces of the foreground that are classified as such by both algorithms, addresses both of these issues and, as you can see, produces the best overall representation of the foreground.
So why do we need foreground extraction? For this answer, we will focus on the application we began constructing as part of our project, a fish classifier.
Without extracting the foreground, our neural network-based classifier may recognize only the scene and classify it too broadly. However, once we extract and segment the foreground, we can begin classifying individual fish.
There are many other extremely important applications for underwater video processing via background estimation and foreground extraction. After retraining the classifier on different objects of interest, this could be used by groups such as marine biologists for counting bioindicators, police departments searching for evidence, or departments of transportation inspecting bridge supports.
Overall, as the foreground extraction runs near real time, we hope that our system will eventually serve as the backbone of multiple applications that users can run directly in the field.